Now we're going to study double integrals and the iterative integrals today. Okay? In the last couple lectures, we are talking about derivatives and how to find the maximum minimum value on a domain with a boundary or without boundary. Okay, it's very similar to functions with room variable. I did not see many students attending class. I hope they are finding time to read the book and do all the homework. Okay. Right, so double integral, what's the definition of double integral? Because the function has two variables. So defined on the domain, defined on a domain could be an arbitrary domain, could be a rectangular domain. And they are, let's begin with a rectangular domain, okay? And the rectangular domain would be much easier to understand at the very beginning. Okay, so we have, this is now let f be a function. I do not assume this is I do not assume it's continuous at this moment. That be a function defined on rectangular domain. Okay, so the domain is called a. This is a D. This is a cross product. Okay, it's written in this form. If I draw the domain here as A and B, C and D. Okay, so you can get a rectangle in the space. Okay. Then, how to define the double integral? How to define the double integral? The idea is it's very simple. You divide the intervals in many subintervals. Okay, so here's a partition. Okay, so A equals x0, x1, x2, and xn. That's B. Okay. Okay. Then I also have here the y1, y2. So y0 is a C, y1, ym, that's a D. Okay. So we have a typical partition. Yeah, let's look at this. So this is there you have you divide a large rectangle into many small rectangles. Okay. So the width of this is going to be delta xi. So delta xi would be xi minus xi minus 1. So the difference of this. Okay. And the delta yi is going to be yi minus y. I use a j. Okay. Yj minus 1. Okay. So the area of this rectangle is going to be called delta aij. This is going to be the area delta xi times delta yj. Okay, so this is the area of the rectangle. This is the area of this sub-rectangle. Okay, you have how many rectangles right now? You have n by m small rectangles. Okay. Then this is so-called calculus idea let's introduce the integral. Yeah. So then you take an arbitrary point inside. I call it xi star. So this is a xi star. Yeah. Let xij star be a point. We have to use two coordinates: xi star, yi star. Yeah. Yij star, okay? Yj star be a point in the rectangle, okay, in this rectangle. Okay. So this rectangle written in the form xij minus 1 xi cross yj minus 1 yj. Okay. Okay, now everything's ready. All right. We consider the so-called Riemann sum. The Riemann sum is going to be sigma. Here's f, the value of xij star, yij star, the value of the function at that particular point, at this point inside the rectangle. And here we delta aij, okay? Delta aij is the area of this small rectangle. So this product, okay, when add them together, I start from 1 to n, okay? We use a W, yeah, and j start from 1 to n. So add all those together. Okay. Now, what's the geometric meaning of this Riemann sum? The geometric meaning of this Riemann sum, if f is positive, this is going to be the volume of that piece under the graph. Okay, so if you look at the picture here, this is an interval. You know, this is it's hard to draw it right now. Yeah, this is a rectangle, right? In the xy plane, and there is a small rectangle here. So the graph is here, right? This is the graph. Z equals f of x, y. So there's a small piece. It's a yeah. Okay. So that piece, this kind of cylinder type. It's a square, a rectangular base, and the height of this one is almost equal to f of x, right? The height, okay? The height is almost equal to f xij star yij star, okay? Right? So the product is going to be the volume, approximation of the volume of this kind of color we call cylinder. Okay, so this is the volume, approximate about the volume. Yeah, the volume and the graph, the three-dimensional region and the graph above this rectangle. Okay, if the function f is positive. Okay, okay, this is geometry meaning. So when you add them together, you get a good approximation of the volume of the whole region under this graph and above the xy plane. Okay, so that's the limit. So we want to talk about the limit. Okay, the double integral is defined. The double integral of this function. Okay, this is our notation. Okay, the double integral of this function. Okay, the double integral integral of f on d is defined to be this limit. F is a limit exists. Okay. So here's the mn goes to infinity. Let's call it Riemann sum. Okay. That's a Riemann sum. Sigma j this is yij star delta aij. Now actually what we need is not just the mn goes to infinity. I want delta xi goes to 0, delta yj goes to 0. Okay, so you have to make sure that all the intervals getting smaller and smaller. Now in the book, maybe we just assume that they have the equal size. If they have the equal size when mn goes to when mn approaches infinity, definitely delta xi y delta yj approaches 0. Okay, so if all those intervals have the same size, then delta x, delta xi is going to be b minus a divided by n. Okay, then clearly when n approaches infinity, then this approaches 0. Okay, and delta yj is going to be c minus d minus c m. Okay, then nm approaches infinity implies delta xi approaches 0, delta yj approaches 0. Okay. Okay. But we are talking about here the original definition of double integral is going to be an arbitrary partition of the interval. But all we need is make sure that the size of the subinterval approaches 0. Okay, so I think this should be the most general definition. Now, what we call the Riemann sum? Yeah, this is a remark. Okay, the Riemann sum. Why called the Riemann sum? Riemann proved that. Yeah, this is Riemann sum. Riemann proved that he was born in 1854. And probably this is his result in 18, maybe 70 something. But Riemann passed away at the age of 39, and he already, he made a greater contribution to mathematics, not only in calculus. Okay? And he set up the geometry called the foundation of geometry called Riemann geometry, which was used by Albert Einstein to express his general relativity theory. So every kids know Albert Einstein, but they probably do not know what Albert Einstein did. Okay, what mathematics he used called Riemann geometry. That's why Riemann is famous in that area. Okay, so Riemann showed that if D is a closed bounded domain, okay, and F is continuous on D, then we guarantee that the limit of the Riemann sum exists. The so-called Riemann sums exists. Okay, it's guaranteed. So it's okay. You're going to find the sum. Okay, and that's it. So this is it's very similar to the theorem for function in one variable. Okay, Riemann did it for function in any variables. Okay, so the limit exists. Then you can talk about the function. The double integral of the function. Okay. So if it exists, because this limit exists for all those possible partitions, as long as the size of the rectangles, okay, approaches 0. Okay, so in particular we have, you can compute this double integral in this case, okay, by the following limit. Okay, you can choose you can choose those special Riemann sum n(i) equals d, and j, from m, here's f, and this is I will mention what is x star. Okay, yj star, and this will be the delta a, and here I choose a special one, right? So the partition will be xi is going to be a plus I delta x, okay? Delta x is going to be b minus a over m. And the yj is going to be c plus j delta y. Delta y is going to be c minus d minus c over m, okay? So those are the special partitions. So delta A is just delta X, delta Y, okay? And this special point can be just an arbitrary point. Special point can be xi, yj, okay? Those are, you can take the one of the endpoints. Okay, look at this interval. Okay, this interval here will be x j minus 1, y j minus, right? And here x j y xi, sorry, xi, and j minus 1. And that will be xi, y, j. That point will be xi minus 1, yj. So you have a 4 vertices of the rectangle. You can just choose one of them. We usually choose that point. Okay, it doesn't matter which point you can choose, and it's guaranteed as a limit. Yeah, the limit can be computed. You can choose a middle point. You can choose a middle point, then you can get a middle point rule for the double integral. Okay, so if you choose a middle point, it will be in the middle. Okay, and that is called xi bar, j bar. Okay, so this can be any of those points. Okay, this can be xi or xi bar, yj bar. Okay, this is a middle point. Okay, that's called the middle point rule for double integrals. Okay, so you can use that to do the computation. But the computation is pretty complicated. You have to use use a limit, right? Let's try use a definition to find the value of the double integral. Okay, so here's a function. Here's a function f(x). I make it easier, just a linear function. Okay, f(x) is going to be x plus y. Okay, and here x is between 0 and 1, y is between 0 and 1. Okay, so our d is the d is actually the interval from 0 to 1. Yeah. Okay. So the function is continuous. I think the function even greater than or equal to 0. So what we get the integral should be can be viewed as the volume of this the volume of this region. Okay. If you look at the picture, it's harder to draw the picture here. Yeah, this is a 3D. That's a x, y axis, and z axis. When x equals 0, y equals 0 is the origin. When x equals 0, y equals 1, it is here. When x equals 0, when y is 0, x is 1 is here. And then, even higher here. Okay, so it looks like, okay. It's not easy to draw that. Anyway, it's like a piece of plane cut through pass through the origin of the coordinate system. Okay. Yeah. So this is clearly it's kind of it's kind of loose attached to one point attached to the ground. Okay. So the limit, the double integral, should be viewed as a volume region. You can even find the volume maybe directly if you want, because you already sketched the graph. So let's do this problem. Okay, I'm going to partition the region. It's going to be 1 over n, right? Delta y is going to be 1 over n. Okay, we use the mn, doesn't matter. So okay, so xi is going to be ni, right? Yj is going to be jm, okay? So I also take this point in the interval is xi, yj, okay? So this is going to be ni, jn, okay? J over m. So now the Riemann sum, okay? F of xij star, yij star, delta aij, right? So let's put the details. Okay, so it's x plus y, so it's I over n plus j over m, okay? And the delta aij is going to be delta x times delta y. So it's 1 over n, 1 over m, okay? So let's try to find the sum, okay? You can multiply this out, so actually you will get I n over m, okay? So plus m j from, this is jm, okay? So this one of, okay? So you separate them. Now you add them together. I think I can get rid of j here because when you add them together, this is just a one m. So actually you end up with I over n squared. Okay, there's no j here. So right hand side, the index here, there's no I. So that's why you will get this, because you will n over n, that's going to be 1. Okay, remember sigma n I from 1 over n is 1. Okay, then we use the formula. The sum from 1 to n is going to be n over n plus 1 over 2. Okay, and here will be m squared, so that'll be m times m plus 1 over 2. Remember, this is a formula, right? The sum of the I is going to be n times n plus 1 over 2, okay? So now, simplified, you will get 1 plus 1 over n. Here you will get 1 plus 1 over m. So when you, clearly this can approaches 1/2 plus 1/2 equals 1. As n approaches infinity, m approaches. So you do get a limit. I know the function is continuous, so the Riemann sum has a limit, and so you can use this special partitions to find the limit. So my conclusion is double integral of x plus y, okay, dA is going to be 1. Okay, and this is actually the volume of that region. Okay, that is the volume of that region. Okay, then we define so-called iterative integral. Okay, the iterative integral is defined in the following way. Okay, iterative integral. Okay, so we assume that f is a function. Okay, let f be a function on the interval d, on the domain and C and D. Okay, so this is a function defined on that, and we have to assume that the function is differentiable for each of first of all, yeah, for any fixed x, right? For a fixed x, you get a function in y variable. So if you fixed y, right, fixed x, you get a function in one variable, okay? So you can integrate from c to d and dy, okay? Right? Then you integrate, this is going to be a function of x. If it's, suppose this is always integrable, okay? Then you can integrate, this is a function of x already. Then you can integrate from, with respect to x. Okay. So you get the w. Okay, this is called the w integral. If one of the integral is not doesn't exist, then the w integral does not exist. But you can also do the following. You can integrate the function with respect to x first, just like a partial derivative. You can integrate, right? Fix the y, then you differentiate f with respect to x, and here integrate with respect to x. And then you get a function of y because the y variable, x variable is gone after you integrate, but y variable is still there, right? Then you integrate with respect to y. So you get two w integrals. Okay, so we get two w integrals. That makes sense. Okay, we're using the idea calculus in one variable, the calculus 1 for the function one variable. Okay, those called the iterative integrals, very similar to the partial derivatives. Okay, that's in the opposite direction. So let's take a look at some examples. Okay, f of x, y. I'm going to still use x plus y for the simplicity, okay? D is going to be from 0 to 1 times from 0 to 1, okay? Okay. So let's finish the from 0 to 1, Here's a x plus y, dy, and dx. Let's compute this, right? Now, what is inside? So we are trying to evaluate the integral function with respect to y variable. With respect to y variable, the antiderivative of that function with respect to y variable will be half of y squared, right? And evaluate at the two endpoints, okay? View x as constant. Okay, view x as constant. Okay, then
shouldn't that be dy?
I begin with no dx here. You see, I already found the antiderivative for this function. For this, I'm evaluating this integral inside with respect to y variable. So y variable is dy is already gone. You know, the antiderivative of x plus y is x times y plus half of y squared. So evaluate the two endpoints. So what you get here is when y equals 1, I get x. When y equals, here's half, 1 half, 1 square. And then when you plug 0 for y, I got 0. So this is what I got. Okay. Then you get the integral with respect to x variable. Then antiderivative of this is going to be half of x squared and plus 1/2 times x. Okay. That's antiderivative function. And evaluate at two endpoints. Right, then you plug 1 for x, you get 1/2 plus 1/2, it's 1. Okay, and minus is, plug 0 for x, you get 0, 0. Okay, so that is answer. Just like, if one by one, evaluate the integral.
I have a question.
Yeah.
The first one, the last line, is that a new one, or are we talking respect to the first equation up there?
You mean the last line?
Where did that come from? The x plus 1/2.
X plus 1/2 is coming from here.
Okay, so that has nothing to do with x plus y?
No, this is already you see, the integral from 0, this is going to be x times y plus half of y squared, evaluated the endpoint, okay? Then it'll be x times 1 plus 1/2 1 squared minus x times 0 plus minus 1/2 0 squared, okay? That's where you get x plus 1/2. Clear?
Okay.
Yeah. So yeah, you focus on that integral. That's the integral with respect to y variable, just like a partial derivative. View x as a constant here. And then you do the, this. But then let's try a different way, okay? We also have another double integral, exchange the order, okay? So I integrate with respect to x first, then integrate with respect to y variable, okay? So it's similar in this situation, right? So antiderivative of x plus y with respect to x will be half of x squared plus the y times x. And then you evaluate the two endpoints, okay? And then you plug them, 1 for x, so it's 1/2 plus, that's y, okay? Okay. And then you have to find the antiderivative of this function. And you evaluate two endpoints, and you get 1/2 plus 1/2 equals what? And it's not surprised. They're equal for this particular function. Not only equal, they also have the double integral. So we got this double integral is going to be equal to the iterative integral, okay, x plus y dy dx, and it's going to be x and the dy. All right, so you can try another function. You find out this is always true. You'll be surprised. Yeah, it is always true. So the double integral, they're all equal to what, okay? And equal to the iterative integral, any of them, okay? Y first or x first, doesn't matter, okay? Then, that was in the history, okay? Then the Fubini, did a mini exercise, then you find out, this is always true. The question is, how do you prove it, okay? So when you did pay attention to the results, you try another function, and you find the double integral, evaluate the double integral by the limits, then you also evaluate the iterative integrals. But you always find out they're equal. Now in that case, in biology, maybe just publish a paper, hey, we discovered this phenomenon. But in mathematics, you have to prove this is always true, okay? Because this is true for a general function, not for this function you just did. But biology says, well, I only did it 10 times, I used 10 different functions, it works. But in mathematics, this is not a result. It's just that you can conjecture if this is true in general. How do you know for another sample, then you still get the same result? And that happens in biology. Sometimes 10 years later, they find out for another new sample, find out the result to be different. Then I have to revise the textbooks. Okay, mathematics, we don't that. Of course, they still revise the textbooks just because I believe that the publishers want to make money. That's my opinion, okay? Otherwise, there's no reason to use a different textbook than your grandparents used, okay? Okay, so Fubini proves this theorem, says that if the function is continuous on rectangular domain, then the above equality always holds, okay? If f is continuous on a D, which is a C and D, A and B, okay? Plus C and D. Then this double integral, according to Riemann, exists, okay? Then this is going to be the iterative integral, okay? So you can C and D first, and A and B inside, and then this is the integral with respect to x first, then dy, and also you can change the order. Okay, that's right. So the iterative integrals, we use calculus 1 ideas, because each time you evaluate integral with respect to one variable, right? And then, of course, you have to do it twice, okay? And with respect to x and with respect to y. And the order doesn't matter if the function is continuous. So here, you see how to evaluate, this gives us an idea to evaluate a double integral, because otherwise, I give you a double integral, how do you do that? You have to use a limit, right? You have to use a limit of the Riemann sums. And for simple functions, you can find the limit of them. But for complicated function, you cannot evaluate the double integral using the limits, because it's harder to find the limit, okay? So what you do is use ideas from calculus 1 to evaluate the single integral twice, okay? Single integral twice, with respect to x and with respect to y, okay? That helps you a lot, okay? So now, that simplifies the idea. Then if you wanted to evaluate a single integral, you can still use a limit, right? The original definition, but we already have many methods here. We have many formulas to do that. That's what we learned from calculus 1. Okay. Okay. So let's take a look at the double integral. Evaluate this double integral of the function x minus 3y squared and dA. And d is going to be from 0 to 2 and from 1 to 2. Okay. So this is a rectangular domain. Okay. But to evaluate, so first of all, you see the function is continuous. And the function, I'm going to use, this is double integral. By Frobenius theorem, this double integral can be, is equal to those two iterative integrals. I can use any of them to evaluate. But in order to check Frobenius theorem, maybe I should evaluate these two iterative integrals. I'm pretty sure they're same. Okay? So by Frobenius theorem, and this is again, let's look at the first, when this is a 0 from 0 to 2, and the y is from 1 to 2, so this should be y first, and then dx. Let's evaluate this in double integral first, iterative integral first. Okay. So this is an integral with respect to y variable. So x is the constant. So the partial antiderivative of this with respect to y is going to be this. Okay, evaluate at these two endpoints. Then I plug 2 for y, and so get 2x 2 cubed minus x minus 1 cubed. Okay. Yeah. So after simplified, I only get x here, 2x minus x, then negative 8 plus 1, so negative 7. Okay. Okay. Then the antiderivative of this function is half of x squared minus 7x. Then I plug 2 squared here minus 7 times 2. Okay. So if I plug 0 for x, I get 0, so don't worry about that. That's 2 minus 14, so it's negative 12. All right. Now, if the computation is correct, then this double integral is going to be negative 1/2. Okay. This double integral is negative 12. Okay. So we claim this double integral, okay, x minus 3y squared dA is negative 12. Okay. By Frobenius, Frobenius. So Frobenius theorem. Okay. And if you just, without Frobenius theorem, how do you find this double integral? You have to find a Riemann sum and take a limit. You still can do that, okay? It's very complicated. It involves a sigma of I squared. Okay. Right. But I want to make sure the Frobenius theorem is correct, right? I I can switch the order of the integral from 1 to 2, x minus 3y squared. I'm going to evaluate the integral and this double integral from 0 to 2 and the dy. Okay. Yeah, let me double check it's correct. Yes. This is another iterative integral, right? There are two iterative integrals. According to forbidden theorem, they must have the same value, and that should be equal to the double integral. Okay. So let's do this computation. We hope we can get the same answer. Okay. X is going to be half of x squared antiderivative, and the 3y squared times x from 0 to 2. Okay. And then dy. All right, so now plug 2 for x. Okay, and I think I don't need to plug 0 because plug 0 for x, you get 0. So yeah, let's simplify a little bit. 2 minus 6y squared dy. Okay, so now the antiderivative of that function will be 2y minus 2y cubed. Okay, evaluate two endpoints. Yeah, 2y cubed because yeah, when you differentiate, you get 6y squared. So let's do this. 2 times 2 minus 2 times 2 cubed minus 2 times 1 minus 2 times. Okay, the second term is 0. I think the second term is 0. So I got 4 minus 16. So it's still negative 12. It's the same answer. Great. So we are verifying, we have a verified forbidden theorem for this problem. At the same time, we evaluate the double integral. Okay. All right, let's take a look at the example exercise from the book. Okay, so we have many problems here. Sometimes you are just asked to find the iterative integral. Sometimes they want you to find the double integral. Okay, let's do problem number. Yeah, let's do problem number 33 or 32. Let's do the problem number 32. Okay, this is a double integral. Sometimes I use a R instead of D. R means region. I'm going to use a D here. X1 plus X times 1 dA. Okay, D is from 0 to 1 and from, yeah. Okay, so this is a square. Okay. First of all, you have to make sure this function is defined, well defined, and I think over that domain, right? Over that domain, x is greater than 0, y greater than 0. So that implies 1 plus xy is always greater than 1. Okay, we are okay because the function is well defined. Otherwise, the function is not even smooth. Okay, it's not continuous if you divide by 0. So that means this function is continuous on the D. Okay, so that means you can apply the forbidden theorem to solve the problem. All right. So by forbidden theorem, sometimes you don't need to mention that always. So you can have you can use a 1 over iterative integral. If you just want to find the double, evaluate this double integral, you just use a 1 of the iterative integrals. Right? It's from 0 to 1, and you can say this is with respect to x variable inside. Okay. You can decide which one you want to use. Okay. If you use the x variable, you find that's a little bit more complicated because you have x variable in the numerator and y variable in the denominator. If you switch it, I think the second one is better because you just need to consider one variable here in the denominator, right? So remember how do you find the evaluate antiderivative, right? It's 1 plus u du, right? It's going to be natural log 1 plus u, right? Right? Now, if you have a constant here, okay, you can use a substitution. So it should be equal to 1 plus au, but when you differentiate, you get another a, so it's divided by a. Okay. You can quickly get that. So now you view x as a constant, okay? So this double integral, yeah, this double integral, you can use a second iterative integral, okay? So the antiderivative of that function with respect to the y variable is going to be natural log 1 plus xy, and evaluate 0, right? And dx. Why? Because when you differentiate, yeah, so when you differentiate, you will get 1 plus x times y in the denominator, and another x is the numerator, okay? So if I change, put an a here, I have another a here. So see, this is what we get, okay? So now it's much easier. One of the iterative integral will be easier to handle. So then you can natural log 1 plus, you plug 1 for u, so it's x, minus natural log 1 plus, it's a 0, and right, it's from 0 to 1 dx. Okay, and then the second term is 0. Now the problem is how do I evaluate this integral? How do I evaluate this integral? We have to use integration by parts. Okay, find the antiderivative of this. Okay, integration by parts. Integration by part. You can get this is a u, that's a dv, right? So v is x, so it's x natural log 1 plus x minus x. You switch the order. du is going to be 1. Okay. Okay. Then you have to find the antiderivative of this function. How can I do that? Well, you have to decompose it. Okay. So you can a plus, the easiest way to do is just add 1 plus 1 minus 1. Okay, plus 1 x plus 1. That is a quick way to do. Okay. So x plus 1 over x plus 1, right, is 1 minus 1 plus x. Okay. Otherwise, you have to x divided by 1 plus x. You still get the same result. Okay. So the antiderivative of 1 is x. So it's going to be x, right, minus this is natural log 1 plus x. Okay. So we find the result. It's pretty complicated. Plus natural log 1 plus x and minus x. I can even combine them, x plus 1. Okay, so that's it. So this is the antiderivative. And then I put into the above integral. So let's say the double integral from 0 to 1, natural 1 plus x dx is going to be evaluated to end point. Okay, I think you just needed to put here, so 1 for x, that's 2 natural log of 2 minus what? If you plug 0, all the terms give me 0. So that's all. That's what we get. Okay, that's what we get. Now, the geometry meaning of, let me repeat again, the geometry meaning of the double integral is going to be the volume, okay? So here's the volume, about the volume. Okay. So if fxy is greater than 0 on the domain, then this double integral from the limit of the double integral, from the limit of the Riemann sums, is going to be the volume of the region. Okay, is the volume of the region in the space. Yeah, it's the volume of the region, and the graph. Okay, and above D. Okay, so if I ask you to find the volume of you can also use this result to find the evaluate double integral. For example, if I ask you to evaluate this double integral, 1 minus x squared minus y squared, and the dA, okay, and D is going to be this circle, okay. Now it's very hard to evaluate this double integral right now without any other methods. So you cannot. It's complicated if we use a iterative integrals. What you should do is you recognize that this is going to be a circle, okay, in the x to y plane. That's a D. And then z equals 1 minus x squared minus y squared is the same as z squared equals 1 minus x squared minus y squared. So you get x squared plus y squared plus z squared equals 1. So this is the graph of this equation is actually the apsemi sphere. Okay, so this double integral is just the volume of the apsemi. We call it apsemi ball. Okay, so this half of the volume of this ball. So this double integral is going to be 1/2 of the volume of the unit ball. Okay, and if you remember the volume of the unit ball, then you can find it, right? So how many of you remember the volume of ball? Okay, was reduced up. Okay, let me record this volume formula for the ball. Okay, then you can. So the surface area is going to be 4 pi r squared. Okay, the volume is going to be 4 pi divided by 3 r cubed. Okay, so that's why this is going to be 1/2 4 pi over 3 and the 1 cube. So it's 2 pi over 3. Okay. So for the sphere, the surface area is 4 pi r squared, and the volume is going to be 4 pi over 3 r cubed. Okay. Actually, this is if this is r, right? Okay, and this depends on the value. Actually, this is going to be integral from 0 to 1, a t and dt. Okay, yeah, this is a very famous formula. The integral of the surface area is going to be the volume. Okay, you can integrate this. Okay, and that's why r t squared, the antiderivative is 1 over 2. 1 over 1/3 times t cubed. That's why you end up with 4 pi over 3 times r cubed. Okay. So this is about my this is a full content. Well, we can talk about the average value of a function in two variable. How do you define the average value of a function in two variable is defined in the same way. Okay, so the average value. Okay, so given function on given function. Yeah, let f be a function on a domain D, okay? Then the average value by definition, okay, we use this notation, AV, okay, AV, is defined as this double integral of the function divided by the double integral of the constant function, which is just the area of the yeah, the area of that domain. Okay, and why it's called the average, because if f is a constant value, then this just equal to the constant. Okay, so it's as long as you know the definition, then you can find the average value. Using the double integrals. So there's nothing new here, just needed to know the definition. So given a function, if you ask it to find the average value, you just evaluate the double integral and divide by the area of the region. Sometimes the area of the region is very simple. It's easy to find out. For example, it's a region is a disk, just the the area of the disk. We have a formula already. Okay. So let's stop here today, and we're going to take a quiz